Hello guys, welcome to my YouTube channel. Let us solve the week 4 graded assignment of machine learning foundation. So the second problem is consider the following statements regarding a real symmetric matrix A. Which of the above statements are true? So there are 6 given statements. We have to tell which statements are true. So if A is a real symmetric matrix, then eigenvalues of A are always real. And the second property is, and eigenvectors corresponding to distinct eigenvalues form a linearly independent set. And third is orthogonally diagonalizable. So the first statement, what is given, the eigenvalues of A are always real. So the first statement is true. And the eigenvalues of A may be imaginary. Not, this is not correct. Third is the eigenvectors corresponding to different eigenvalues of A are linearly independent. So this is true. The eigenvectors corresponding to different eigenvalues of A are not linearly independent set. We have seen if the eigenvalues are different, then the corresponding eigenvectors will be linearly independent. So the third option is correct, not fourth. And if A is a real symmetric matrix, then A is orthogonally diagonalizable. So this is correct. This is also correct. So first, third and fifth are correct. You can see the solution, and let us proceed with the next problem. The third problem is the eigenvectors corresponding to distinct eigenvalues of a matrix. So we have seen in the above example, if eigenvectors corresponding to distinct eigenvalues of a matrix are linearly independent. So the first option is correct. You can also see the solution of this. You can prove this. If suppose c1x1 plus c2x2 equals to 0, and we have multiplied both sides with matrix A and separated the coefficient c1ax1 plus c2ax2 is equal to 0, since lambda 1 is the eigenvalue and x1 is a corresponding eigenvector, so a1 x1 is equal to lambda 1 x1, and similarly ax2 is equal to lambda 2 x2. So we have rewritten the above equation, c1 lambda 1 x1 plus c2 lambda 2 x2. And now in this first suppose c1 x1 plus c2 x2 is 0. In this equation we have multiplied by lambda 2. The corresponding equation will be lambda 2 c1 x1 plus lambda 2 c2 x2 is equal to 0. We have subtracted the second equation from first, and we got this. So c1 x1 in bracket lambda 1 minus lambda 2 is equal to 0. So here it is given that the eigenvalues of A are lambda 1 lambda 2 are eigenvalues of A with corresponding eigenvectors as x1 and x2, and it is given that the eigenvalues are distinct. The distinct eigenvalues, it is given that in the problem. So lambda 1 does not equal to lambda 2. So for this to be 0, we have c1 is equal to 0 in equation third. Similarly c2 is equal to 0. Therefore x1 comma x2 form a linearly independent set. So hence we can conclude that eigenvectors of corresponding distinct eigenvalues of a matrix are linearly independent. So in general way we can prove this also. And let us solve the fourth problem. The determinant of a 3 cross 3 matrix having eigenvalues 1, minus 2 and 3 is, so by properties of eigenvalues we know that determinant of A is equal to product of eigenvalues. So we can let us suppose the lambda 1 lambda 2 lambda 3 are 3 eigenvalues of 3 cross 3 matrix. So the determinant of A will be lambda 1 lambda 2 lambda 3, and it is given that lambda 1 is equal to 1, lambda 2 is equal to minus 2, lambda 3 is equal to 3. So we can calculate the value of determinant as minus 6. So you can tick fourth, D option is correct. So let us proceed with the next problem now. The determinant of A will be lambda 1 lambda 2 are eigenvalues of 1, lambda 2 are eigenvalues of A with corresponding eigenvectors as x1 and x2, and it is given that the eigenvalues of A will be lambda 1 lambda 2 lambda 3 are 3 eigenvalues of 3 cross 3 matrix. So the determinant of A will be lambda 1 lambda 2 lambda 3 is equal to 1, lambda 2 is equal to minus 2, lambda 3 is equal to 0. So we have The next problem is the trace of a 2 cross 2 matrix is -1 and its determinant is -6. We have to calculate the eigenvalues of 2 cross 2 matrix. So again, by properties of eigenvalues, determinant of A is equal to product of eigenvalues and trace of a matrix is equal to sum of eigenvalues. So it is given that determinant of A is equal to -6 and trace of a matrix 2 cross 2 matrix is -1. So to find lambda 1 lambda 2, we have a two equation by properties of eigenvalues. Lambda 1 multiplied by lambda 2 is equal to -6, and by using the properties of trace of a matrix A is equal to sum of eigenvalues. So lambda 1 plus lambda 2 is equal to -1. We call this second equation, and from equation 2 we have rewritten the value of lambda 2. Lambda 2 is equal to -1 minus lambda 1. So now we will substitute the value of lambda 2 in equation 1 in this equation. So by substituting the value of lambda 2 in equation 1, we have lambda 1 in bracket -1 minus lambda 1 is equal to -6, and by rewriting the above equation, minus lambda 1 minus lambda 1 square is equal to -6, and we have factored the equation and got the value of lambda 1 is equal to -3, 2. So for lambda 1 is equal to -3, we have lambda 2 is equal to -1 minus lambda 1, and by substituting the value of lambda 1 is equal to -3, we got lambda 2 as 2, and vice versa. If we substitute the value of lambda 1 as 2, we got the lambda 2 is equal to -3. So in both ways, the values of the eigenvalues of matrix A are 2, -3. So we can say that the third option is correct. So this is the correct option. So now proceed with the next problem, problem number 6. What it says? It says if the eigenvalues of a matrix are -1, 0 and 4, find the trace of a matrix. So we have seen by properties of eigenvalues we can say that trace of a matrix equal to sum of eigenvalues. So it is given the lambda is equal to -1, lambda 2 is equal to 0, lambda 3 is equal to 4. So the trace of a matrix will be a -1 plus 0 plus 4 is equal to 3. So the trace of a matrix is equal to 3. So let us proceed with the next problem, question number 7. It says if the eigenvalues of a matrix are -1, 0 and 4, find the determinant. So again, by the properties of a matrix, eigenvalues, determinant of matrix will be product of eigenvalues, and the eigenvalues of a matrix is given as -1, 0 and 4. So determinant of matrix will be, since the value of second eigenvalue is 0, so the product ultimately will be 0. So the determinant of matrix will be 0. So let us proceed with the next problem, problem number 8. And the characteristic polynomial for the matrix A is equal to 1, 1, 1, 3 is. So to solve this problem, the characteristic polynomial for a 2 cross 2 matrix is equal to lambda square minus trace of matrix lambda plus determinant of matrix. So in general way, we can also solve this problem using determinant of a minus lambda is equal to 0. So in shortcut way, we can also solve this problem using this property. It is only true for 2 cross 2 matrix. For 2 cross 2 matrix, the characteristic polynomial will be lambda square minus trace of a matrix. Trace of matrix is this, the sum of this, plus determinant of matrix. So the for 2 cross 2 matrix, the trace is equal to sum of diagonal elements. So the trace is equal to 3 plus 1 is equal to 4. So we can solve this problem. Lambda square minus 1 plus 3 lambda plus determinant of a matrix 1, 3 minus 1, 1. So this is a 2. So this is 2 and trace of matrix. So ultimately the answer of this problem is minus lambda square minus 4 lambda plus 2 is equal to 0. So let us solve the next problem, the problem number 9. What it says, the eigenvalues of a matrix are. So for the same problem, I think the same above problem, we have to find the eigenvalues of a matrix. So we have calculated the characteristic polynomial of a matrix of a matrix A. So again we will solve the problem by solving the first characteristic polynomial, then we find the value of lambda. So the characteristic polynomial will be lambda square minus 4 lambda plus 1 is equal to 0. So to solve the above quadratic equation, we will use the quadratic formula, which is in general x square plus bx plus c is equal to 0. The quadratic formula is x equal to minus b plus minus in under root b square minus 4ac upon 2a. So we will use this formula and solve the value of lambda, and finally we have solved for lambda and got this lambda is equal to 2 plus minus equal to root 3. So the lambda 1 is equal to 2 plus root 3 and lambda 2 is equal to 2 minus root 3 are the eigenvalues of A. So let us solve the 10th problem of this series. If the eigenvalues of a matrix A are 0, minus 1 and 5, the eigenvalues of A cube are. So in this problem we will use the property. What is the property? We know that S inverse a की power k s is equal to lambda की power k, where lambda is eigenvalue of a matrix. So or a की power k x is equal to lambda की power k x. So we will use this property and solve this problem. So in general, for a matrix A x1 is equal to lambda 1 x1, and ax1 we have a for first eigenvalue lambda is equal to 0, and let us say that lambda 1 is equal to 0, and we substitute the value of lambda 1 and 0 x1, and we have used this property a की power k. So the we have asked in the problem we have to find the eigenvalues of a cube. So we will solve this. A cube is x1 is equal to lambda 1 cube x1, and here lambda 1 is equal to 0. So we will solve 0 की power cube x1 is equal to 0 x1. So here the value of lambda 1, the value of the first eigenvalue of a cube are 0. Now we will solve the we will again use this property for eigenvalue minus 1. So again we will solve x2 is equal to lambda 2 x2, and a cube x2 is equal to lambda 2 power cube x2, and we substitute the value of lambda 2 as minus 1 minus 1 की power cube x2, and here is minus 1 x2. So the second eigenvalue for a cube is minus 1. Again we will solve for lambda is equal to 5. So for lambda is equal to 5, a cube x3 is equal to lambda 3 की power cube lambda 3 की power cube x3 is equal to 5 की power cube and x3. So the value of lambda 3 for a cube is 125. So therefore the eigenvalue of a cube are 0, minus 1, 125. So let us solve the 11th problem of this series. The 11th problem says the 110th term of Fibonacci sequence is approximately given by. So for 110th term we will solve this problem using this formula. So in general, the kth term of Fibonacci series is given by 1 by root 5, 1 plus root 5 by 2 की power k minus 1 by root 5 in bracket 1 minus root 5 by 2 की power k. So for 110th term being a very large number, so we can ignore the second term. So the second term in fk becomes negligible and is ignored. So this is a very less value, approximately 0 for large value of k, and we can ignore this term. So for 100 term 1 by root 5 in bracket 1 plus root 5 by 2 power 110. So the final answer is this. Let us solve the 12th problem. Let A be n cross n matrix, which and we have asked which of the following statements are false. So there are 4 statements given. This is a MCQ question, so more than one can be correct. We have to find which of the statements are false. So let us proceed with the option A. If A is equal to n cross n matrix, then rank of A plus nullity of A is equal to n. From rank nullity theorem we can say rank of A plus nullity of A is equal to n. So nullity is a dimension of kernel where all vectors V are of form AB is equal to 0. Therefore rank of A is equal to n minus from this equation rank of A is equal to n minus dimension of eigenspace corresponding to 0. So null space by using the property of eigenspace, dimension of eigenspace corresponding to 0. So if if a matrix A has r non-zero eigenvalues, so the rank of matrix will be less than or equal to r. So it can be lesser than or in case some of the non-zero eigenvalues are identical. If the eigenvalues are identical, then corresponding eigenvectors will be linearly independent. So the eigenvectors corresponding to distinct eigenvalues are linearly independent, and since rank of matrix is number of linearly independent vectors, so hence option A is true, because it says if A has r non-zero eigenvalues, the rank of A is at least r. So it can be less than r, so it is correct. If the eigenvalues are distinct, then the rank of A will be r, exactly r, and if some of the eigenvalues are same, then the rank of matrix A will be less than r. Okay, so this is correct. This statement is correct. So let us proceed with the next option. Next option is if one of the eigenvalues of A are 0, then the determinant of matrix will be does not equal to 0. If one of the eigenvalues of A are 0, then we can use this property, product of eigenvalues. So therefore determinant of matrix will be 0. So hence option B is false, because it says not 0. So here we got 0, so the option B is false. And for third option, what is third option? Third option says if x is an eigenvector of A, then so are all the multiples of x. So if if Ax is equal to lambda x, multiplying both sides by scalar k, we got this equation. And if x is an eigenvector of A, then so all or multiples of A will be eigenvector of A. We can, if we multiplied any constant, then that also will be eigenvector of A. So this is also correct. This statement is also correct. This is wrong. This is correct. And what is what is the last option is if 0 is the eigenvalue of A, then A cannot be inverted. Okay, let us see this. If 0 is the eigenvalue of A, then determinant will be 0. And since A inverse is equal to 1 by determinant of A and adjoint of that matrix, and if determinant of A is equal to 0, then A inverse is undefined because it is in denominator. So if a determinant of A is 0, the A inverse matrix and the matrix inverse of that matrix is not possible. It is undefined. So A cannot be inverted. Hence option D is also true. It says A cannot be inverted. So this is correct. This is also correct. So what is asked? Which of the following statement is false? So the option B is false. Okay. Our final answer is this. All other options are correct, only B option is false. So let us solve the next problem. So the next problem is the eigenvalue of matrix R. So again the characteristic polynomial will be lambda square is the sum of the trace. Some trace of this matrix is 4 plus 1 is equal to 5 lambda, and determinant of determinant of that matrix. So the determinant will be 4 minus 4 is equal to 0. So the lambda square minus 5 lambda is equal to 0. By taking this lambda 1 is outside, we got lambda 1 is 5 is equal to 0. So the value of lambda will be 0 comma 5. So the eigenvalues of the matrix are 0 comma 5. Let us solve the 14th problem. For the matrix given in the previous question, so for this matrix 1 2 2 4, which of the following vectors are eigenvector? So the values of lambda for the above matrices are 0 comma 5. So for lambda, let us solve for lambda is equal to 0. For lambda is equal to 0, a minus lambda I x equal to 0, and by solving this we got 1 2 2 4 x1 x2 is equal to 0 comma 0 0 0, and by applying row operation in row R2 in second row, we got this, and by solving this equation by this matrix equation, we got x1 plus 2 is equal to 0, and suppose x2 is equal to k, then x1 is equal to minus 2k, and hence we can convert this equation into matrix form x1 x2 and k is equal to minus 2 comma 1. So the option B is correct. Option B is correct because it says eigenvector as minus 2 comma 1. Okay, for lambda is equal to 5, again a minus lambda is equal to 0, and by solving this equation, we got this, and by applying row operation R2 in second row, we got this, and by converting the above matrix equation into linear equation, we got minus 4x1 plus 2x equal to 0. So again, let us suppose x2 is equal to k, the corresponding x1 value will be k by 2, and again we converted this eigenvector as x1 x2, and by taking common k half 1, and by again multiplying by scalar 2, we got new constant k dash, and the matrix corresponding eigenvector will be 1 2. So hence eigenvectors are minus 2 1 and 1 2. This is the final answer. Let us solve the 15th problem. Suppose that A, P are 3 cross 3 matrices, and P is an invertible matrix, and if P inverse AP is equal to this matrix, then the eigenvalues of matrix A square are. So we have seen that P inverse AP is equal to lambda, and it is given, we have given minus 1 0 3 0 3 8 0 0 4. The diagonal values of P inverse AP correspond to lambda values of A, and so the lambda, so these are the values of eigenvalues. This is lambda 1, and this is lambda 2, and this is lambda 3. So we know that a for kx, in previous question we have also used this property, a for x is equal to lambda for kx. So the eigenvalues of a square are ax1 lambda 1 for lambda 1 is equal to minus 1, a square x1 lambda 1 square x1, and we substitute the value of lambda 1 as minus 1 and 1x1. So the corresponding eigenvalues of a square are 1, and again we'll solve for lambda is equal to 3. For lambda is equal to 3, we got a2 x2 a square x2 plus lambda 2 square x2, and we got 9x2. So the for second value of lambda is equal to 3, the corresponding eigenvalue of A square is 9. And similarly for third eigenvalue, which is lambda 3 is equal to 4, we will again use this property, and A square x3 is equal to lambda 3 square x3, and we substitute the value of lambda 3 as 4, and we got 16x3. So the eigenvalues of the final eigenvalues of matrix A square are 1, 9, 6. Okay, and let us solve the last problem of this assignment, which is the best second degree polynomial that fits the data set, and we have given the value of x and y, and we have to find the best second degree polynomial. So let us suppose my second degree polynomial is theta naught, the theta 1x plus theta 2 x2 square. So we will substitute the value, the given value of y and x. Let us suppose the first is x1 as 0, y1 as 0, this, and we will substitute the value of y1 x1. Let us not substitute this, and in standard way we can write this as. And for second data set, for second point we will write this, and for third point we have given three data points. So for third we will y3 is equal to theta naught theta 1 x3 plus theta 2 x3 square, and let us convert these three linear equations into matrix form. Let us suppose this y is equal to yx function of x, that is, and theta transpose theta is theta 0, theta 1, theta 2. So the transpose of that matrix will be theta 0, theta 1, theta 2. So we will solve this problem using theta 1, theta 2,